Again, thank you for coming today. My name is Lee Goldberg. I'm an editor, a technology editor at Electronic Design magazine, and a recovering engineer myself. And today we're going to be talking about how to build an AGI in your spare time with materials you can find around your home. And our speaker today is going to be Dr. Aliana Marin, who has been doing AI research for how long have you been at this now?
Since I was a child, so to speak.
Yeah, right. Yeah, over 20 years, I know that.
Longer than that.
Yeah, much longer actually. Anyway, so so before we begin, I've got just a couple of housekeeping things. I'll read them off my list. So if you see me glancing down, I get a favor to ask. This is the first time that Dr. Marin will be presenting the results of her research to the general public. So she's asked me to see if anyone here would be willing to shoot a few pictures of us, of the talk while it's in progress. If you do afterwards, I'll give you my card and you can email them to me, and don't feel obligated. It's not a big thing, but it would be really nice. Next, I want to let you know that we only have about 50 minutes or so if we want to have some Q&A, and from past experience, the Q&As are the most valuable thing here. So we've got a bunch of very new, exciting, and previously unexplored territory to cover. So we're going to be throwing a lot of stuff at you very fast, some of which will be familiar, a lot of which won't. But I think it's going to be very exciting. And fortunately, my experience with TCF attendees in the past is that you're all pretty bright. So I think this will be fine. And let's see, we'll have some questions to answer at the end, and we're going to have fun. So strap in. In the event of a classroom depressurization, the oxygen mask will fall down from the top of the thing, but strap in, get your seatbelts tight, and we're going to prepare for takeoff. Dr. Marin, you ready?
Absolutely.
Okay, so we've been talking about your work, various aspects of your work in AI for over 20 years. Well before this was like a popular buzzword, right? I remember, when it was. Anyway, but now that the artificial general intelligence is a hot topic, can you quickly explain the difference between classical AI that you were working on and this whole idea of AGI?
Okay.
And why you don't think any of the big players with current technologies have achieved anything close to a true AGI, well, at least not yet.
They haven't yet, and almost they're sort of avoiding the issue because of the current hoopla over generative AI. And by the way, before we get really, really rolling, first of all, a big thank you to you, Lee, for being man on the ground with this and coordinating, being point man for everything, to Al Katz for the long-term organization at the TCF, and to all of you folks who've been sacrificing your lunch breaks, your evenings, your weekends to do the organization. I know that doing an on-the-ground live thing combined with a virtual is an extra tech challenge and greatly appreciated. So thank you to all of you. So here we are, AGI. We don't have it yet. What we have are two kinds of AI, and I'm going to call them actually pre-AI. Generative AI is still a pre-AI. And the best thing about generative AI as we're seeing it today, and by the way, we've got an upcoming talk after me. I had a chance to see some slides looking great. And definitely you're going to get a very solid fill in on the state of the art for generative AI. But the best thing about generative AI, where we are right now, and Lee, next slide.
Okay, hold on.
Yeah. The best thing that we're seeing with generative AI, for example, the LLMs, there's several different kinds of generative AI, and you'll actually get some of that in the next talk. Several kinds, and right now LLMs are pushing, they're over a trillion parameters, and what that is so beautiful for us is that they're giving us an instance of what the capabilities are when we've pushed it this far. And if we know that at a trillion parameters and counting, we still have major problems, that lets us know the limits of simple, we'll call it signal processing AI. It's taking signals, and it's a lot like what you have with your phone when you start typing in a text message and then it starts offering you the next possible set of terms. It gives you 3 choices, then you pick one, and it gives you the next one and you pick one, and it's playing that rolling forward game. That's very similar in feeling, not exactly in nature, but to large language models. They're very probabilistic based. Okay, let's keep rolling. So we're going to have a few slides here where what we talk about are some of the very well known, if you've been paying attention to the news at all, I'm sure you have, instances of like, oh my God, how did it manage to do that? And Gemini 1.5 is a classic case of getting launched and oh my godness. Mostly, we're talking about the image components, mostly because it overly applied woke rules. So when asked to generate specifics where we know from historical context that certain kinds of person types would apply, it creates different kinds of persons. Okay, let's keep rolling. And this is a really one of the best of the bloopers. A 17th century physicist. Yep. Very woke. Okay, now this is a little bit more detailed. I was putting together a content page for the Themesis website recently, and Themesis is a combination of of 2 Greek goddesses. Themis, goddess of good counsel, wisdom, getting your house in order, and Nemesis, which is what happens when you don't pay attention to Themis. And I asked Google for some instances on or some background on Nemesis, and I was using that material, and then it's like, ooh, 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 what just happened here? Because they conflated. Now, you can't get the same results right now because they keep changing the underlying mechanism a little bit, tweaking it. But all of a sudden, in that one series of paragraphs, they were putting down the Greek goddess and then a character that was obviously coming out of some sort of it was a role-playing game or an online game or something like that. It was like, whoa, she does not belong in with the classic Greek goddess. Uninformed as these LLMs are and running strictly off probabilities, which they are, they tend to conflate ontologies and mosh things together that have really no business being moshed. They should be separated out. Okay, next slide. And this is one of the best bloopers of recent times. Somebody was asking, and it wasn't Gemini, it was, I think, just basic chat GPT. Is the Great Dane larger than the Mini Cooper? And if we go online and check dimensions, which I did, we know. And there's even cute little stories on trying to stuff your Great Dane into a Mini Cooper, which is sort of a problematic issue. But the chat GPT was saying, oh, the Great Dane is significantly bigger than your Mini Cooper. Okay. Go.
So we're gonna go to the next slide.
Yeah,
But
yeah.
before we do,
Yeah.
we get a question here.
Yeah.
See, from what you've seen here, you really, for some peculiar reason, think that LLMs have some inherent shortcomings that make them unable to exhibit true AGI characteristics alone. So where could you expand further on the architectural shortcomings that cause AGIs to fail so regularly in real world environments, and can we fix them, or do we need to have a completely different approach?
Well, first of all, we need a completely different approach. And
Great Danes are cuddly and Coopers are really cute, but yeah, all right, okay.
and we'll get into that because we've got some actual architecture slides towards the end, and that's going to be where the fun part is. But a quick word, very quick word on generative AI. If you look at the mathematics, the statistical mechanics, the information theory behind it, the founding 3 elements are the reverse Kullback-Leibler divergence, Bayesian probabilities, and statistical mechanics. What transformers, which are the foundation, that's the algorithm underlying all the LLMs, add in are something called multi-head attention and positional encoding. And let's go to the next slide.
Oh, okay, so just in case some of the people are as AI blind as I am. By Transformers, I assume you're not thinking about those huge hulking
Oh, God.
Autobots in science fiction movies.
I am so glad you mentioned that. Thank you. Yes, yes, yes. Transformers. Transformers are an AI, generative AI architecture. And they are the kind of thing that is the baseline for all the large language models, for all the image generation, the image diffusion capabilities. They're all based out of a single algorithm that's generally referred to as a transformer. Yeah. And what we see here is several baseline kinds of generative AI, and I've got to reference the upcoming talk. Who will that speaker will talk about GANs, generative adversarial networks, which are another. They're a spin-off. Do I have it here? When you see in the left-hand side, energy-based neural networks, restricted Boltzmann machines, those are a contributor to the GAN. So you can see how these architectural elements will play together. Variational inference. That's when, for example, you're trying to train a self-driving automobile to understand what's in its field of view. And because you can't properly train on all the possible things that could happen, the notion of variational inference is that you sort of broadly model the space of possible things. Variational autoencoders are a different kind of encoder from the energy-based neural networks. Distinct yet similarities. So those three things emerged beginning like early 2000s up through, I'd say, mid 2015 timeframe, 2016, Transformers 2017, and then everything started picking up steam massively.
Just before we go on, I'm going to just throw a slight curveball.
Yeah.
If you have a minute,
Yeah.
this is where I kept stubbing my toe. Energy-based neural networks. When you were beginning this research and you're talking about thermodynamics,
Mhm.
and I'm sitting here trying to bend that, fold that into what I understood about AI, I was like, I was starting to get brain bleeds. Could you just give us a minute on what energy-based is and why thermodynamic theory and all that just is so important and such a crucial element of some of this stuff?
Thank you so much for asking. Thank you. Thank you. Okay. Puppy dance here. Perfect question, perfect time. Okay. Most people who are studying neural networks don't get into the founding methods for generative AI. And the reason is that it involves, and that's well before you get to transformers. We're talking the energy-based stuff. That and all these other methods, variational inference, variational autoencoders, they all involve, and these are in the previous slide, the reverse Kullback-Leibler divergence, Bayesian conditional probabilities, and then statistical mechanics. And the reason that it involves statistical mechanics, really, really quick, but statistical mechanics involves something called free energy, specifically free energy minimization. Free energy minimization is where you try to take the equation down to its minimum point by adjusting parameters. And the beauty of it is that it's largely controlled by an entropy term, and negative entropy. Negative entropy is bowl-shaped. When you've got that bowl-shaped thing, you've got a minimum, and we're trying to hit that minimum. And it gets a whole lot more complex. But when you read the literature, there's all these references to free energy and other things purely out of stat mech. And the challenge for people coming in is the fusion of disciplines. So Lee, you've actually given me forgive me, but opportunity for a little promo. At the end of this talk, we show how to get material out of Themesis, my company. We have all kinds of educational resources. We have lots of freebie resources on generative AI. We have YouTube playlists. Themesis Inc. is the playlist, is the YouTube channel, Themesis Inc. Multiple playlists, some on generative AI, some on AI education, some on just pure sheer energy-based neural networks. Please go there because you can get greatly enriched just by spending a few hours watching those. And if you go to the themesis.com webpage, there are On the resources page, there's links to resources, collections, including book chapters that are pretty good for taking a person into that whole energy-based neural networks. We have a short course on all these three mechanisms, the reverse Kullback-Leibler, Bayesian, and statistical mechanics, and how they combine to give us generative AI. We're starting that next cohort in the short course, Monday the 25th, and a flash sale price is still in effect. So if you want to self-educate, there are fabulous resources ranging from free to a very interactive, very much like me in the loop, talking with you every week, having a chance to ask questions and have my undivided attention on you.
And at the risk of appearing like a complete nutshell, if you don't get the link, I'll give you a card. I can forward you whatever you need. So let's shall I next slide?
Yeah, move. Okay, transformers. In a left-hand side, restricted Boltzmann machines, core working engine of, and the first thing to emerge in energy-based neural networks, statistical mechanics. It's modeled on statistical mechanics called a special equation called the Ising equation. And the nodes in the neural network are modeled on units, nodes, atoms, whatever, in a contained volume in this space that you're modeling with statistical thermodynamics, where in a physics sense, the spins can be up or down. In transformers, every node has multiple options for being up and down. We can say that it's a multi-head attention. Really, it's a vector space for the spins. And next slide. And the sinusoids on the right-hand side don't show that well, but think of it as every head, every vector spin accesses a timeline of different sinusoidal weightings so that they can be most preferentially accessing information in the recent past or all the way out to the very far past, depending on which sinusoid a given head is paying attention to. And that's where you're finding the actual probabilistic connections of one thing versus the input to the neural network that is the actual transformer or the large language model.
Next.
Yeah, next. Okay, so summing it up. Thinking back to the previous slides where we were looking at like, oh my God, how did it make that mistake? Isn't that just a great big blooper? And the reason that we're getting bloopers and we're getting all in an uproar about them is essentially they're a really simple, restricted model. Not dissing them. I mean, it's a good equation. It's a good algorithm, beautifully enacted by multiple companies, throwing lots and lots and lots of money and energy resources and computers and parameters into the mix. But essentially, it's a simple model that doesn't really describe what we need. It's a form of Ptolemaic or geocentric astronomy. And when you have a massive fiasco scale blooper like Google did with Gemini 1.5, it's because they are overly applying some controls to it. And that's a lot like what you had with Ptolemaic astronomy, where it didn't quite work and they kept introducing little corrections and it just crumbled under the weight of its connections. The problem was that the model wasn't correct. We don't live in a geocentric world. We live in a heliocentric or sun-centered world. And once the Roman Catholic Church allowed the scientists to express certain points of view, and we could switch that perspective from geocentric to heliocentric and say, oh, now we've got a different working model. And once Kepler was able to introduce elliptical orbits, everybody settled down and said, okay, now we've got something that works. And what we've got to do now is get out of the LLM transformer-based models into something that works. We're not there yet. And what we're showing right now are the limits.
So given this perspective, what does that say about where LLM-based AI architectures are along the path towards a true AGI?
They're a fabulous instance of taking something to its limit. And now that we know what the limit is, and we've pushed trillions of parameters at it, And we pretty much have figured out that, another trillion or so parameters will not make a big difference. It's like we're being forced to look at the other possibilities. Whereas up until now, people could have said, okay, if a billion parameters don't work, let's try tens of billions, hundreds of billions, trillion, and see if that doesn't get it. But we're kind of seeing the limitations. And that's the best thing about what we've got right now. We know we're going to have a major shift, and it's right on us. So here we go. This is the major shift. Symbolic processing AI, which has been around for forever. Absolutely. By the way, AI as we know it today, it's a 50-year-old evolution. The big breakthroughs were 1974. Paul Werbis invented backpropagation, and a precursor to the Hopfield neural network, that was the William Little network, which was the same equation picked up by Hopfield later in 82. And then adapted by Geoffrey Hinton to make the first Boltzmann machine in 1983. That was the breakthrough in the signal level processing. But along the same time, and even precursor to that, there was symbolic AI, and the two have never met. And that's our fundamental issue. The two don't meet. So let's have that next slide. Okay, so Google's knowledge graph is the best instance in the world of a really fabulously beautiful, well-worked, symbolic level AI. It's not as shiny these days. It's not like because you can't get in there and interact with a knowledge graph. But when I looked up, for example, the Trenton Computer Festival and got that, you do it all the time. You type in a very specific noun phrase into the Google search, and you get off on the right-hand side this little box. It's a slice out of the knowledge graph. And you get some pictures, and you get slots filled out. So if it's a person, you get the day that they were born. If they're still alive, they don't give a death date. But if they previously died, you get the date of death. You can get their titles. You can get what they are most famous for, who they're associates with, all kinds of information that's put into slots. And the thing about symbolic AI, it's sort of like an encyclopedia or a major filing system. Depending on the kind of thing that you are representing, you have different slots. Let's see that next slide. So you're putting in details. Now, when you have a very specific instance, like a city, and let's just take that next slide.
Okay.
Okay, there we've got Paris. The only reason that we don't have Trenton in this window here is that somebody at Google really loves Trenton, because when you type in Trenton, New Jersey into Google, you get this beautiful across the page knowledge graph. There's a slideshow of pictures, not just one, but a beautiful long slideshow. There's all kinds of details. It's very rich. Paris is actually a little bit more conservative in the Google Knowledge Graph presentation. So when you have something like a specific city, you start putting down things like, I think we see the location, the population, other specific city-related things. So the kinds of slots that you fill in are very specific. Are you talking about a city, the Trenton Computer Festival, a person? So what Google has done, they've spent well over a decade, hugely over. I have no idea of how much money, computer programs, obviously, but they've invested people. We've had people on Google's payroll who've been checking these things and finessing the results. And especially when you've got long-term stable things like when a city was founded or where it's located, those things don't change. So they're worth validating and making sure they're very precisely right. This is, go ahead.
No, I was gonna, so now that we've looked at all of the ingredients, why is it that we don't quite have the cake that we're looking for?
Yeah, because it's hard to connect them, because it's really tricky hard. Because if it was easy, it would have been done. It would have been done 10 years ago, But it is a new thing, and it requires a new approach. And the one thing that's characterized AI over the past 50 years, because we do have a solid 50-year history, 1974, we'll call that the birth of neural networks, including the energy-based, including the predecessors to the current generative AI. And At that time, symbolic was already going strong.
I assume you want the next slide.
Yeah, we're good. We're
Yeah,
good.
there you go.
And, these are two entirely different worldviews, mindsets, computational approaches, different realities, different dimensional universes, and they just don't connect. There's this sort of brick wall that separates the two. And right now, if we're going to make AGI happen, we have to connect the two. And let's just take that next slide.
Hold it.
Okay, so first thing we've got to do for AGI, we got to connect the two. Absolutely. No matter what method we choose, we've got to connect the two. Now, let me just take a moment here. If you happen to go back and read that original transformer paper, we're talking about the paper Vaswani and colleagues out of Google Brain 2017. This is the one that is the great big breakthrough on all the large language models. And they published it openly. Google Brain was fond of publishing their work. And I'm sure that the Google managers have been kicking themselves regularly for the past couple of years on this, but everybody, of course, has read that paper. There's gazillion fabulous little tutorials up on medium.com and all sorts of places. You read that paper, and it's real clear that the problem that they're trying to solve is one that was addressed by two prior kinds of neural networks. One is recurrent neural networks. That was an early invention. Paul Werbus, in fact, the inventor of backpropagation, was dealing with this. This is like, ancient history ago. And then slightly more recently, like last 10 years, long short-term memory networks, which are a way of trying to keep a neuron. You can see it in that bottom layer. That middle layer is where you've got latent nodes, and you would try to keep a latent node, which is where you aggregate information from the input and try to form features. You would keep that active for a period of time on certain conditions. So it was a very artificial, hokey, I'd call it a Ptolemaic tweak, one of these trying to make something work that isn't really meant to work mechanism. It did beautifully. I've had students combine LSTMs with convolutional neural networks and create great results, but still, it's a step along the path, not a long-term solution. And you could see that the people doing transformers, because they explicitly reference those two things, are trying to say, okay, we've got a better approach to temporal memory, because that's always been the big thing in neural networks. It's temporal memory. It's how do you present something? Because we're talking signal processing. How do you present a signal? It goes from the input layer into a feature detection layer, which is latent nodes, which is where you learn to detect combinations of signals in the input. And you get several different features that get activated, and then you combine those to give you your output. I'm simplifying, of course. But in that latent layer, what you want is ultimately you want some temporal memory. But the way that most of our neural networks work is you give it a signal, your feature layer neurons, those nodes, aggregate the information from the signals. Each of them does a different kind of aggregation. They each learn a different feature, and they put their information up to the next layer, say an output. And then the next signal comes in and they do it again, but they've forgotten what happened just a moment prior. And every time they get something new, they forget what happened. And that's why it was so important to have this transformer invention. But transformers are limited. We've just seen that. You're not going to get AGI out of that. What we need is something that will have temporal memory persistence. And that's where this invention called CORTECONs, content-retentive, temporally connected neural networks. It's my invention, based on equations that were developed in the 1950s and 70s, and hardcore, pure sheer statistical mechanics. Nobody wants to do it up until now because nobody wants to learn the equations. But the physics and the math have been worked out. There's preliminary code. There's stuff going on that you can actually play with. And if you, I know, shilling for the company here, but if you go to the Themesis Incorporated YouTube channel, check on CORTECONs, and I think there's a whole playlist on CORTECON code. There's like code access, a walkthrough, demonstrations, an experiment that you can do. The next big YouTube that we're going to put out will be another demo where you can go hands-on and play with this mechanism. and, experiment to your heart's content with this thing. And it's easy, by the way, pure, sheer, raw Python. So you need to connect the two, and CORTECONs are a mechanism to retain temporal memory so that you can have input into these ontologies over time, because you don't want to just like one input and then you're done. Identifying that the ontologies that we're talking about typically takes multiple passes, unless you just got like a simple query. So let's go ahead. And Leslie, you want to ask a question?
And, I mean, it's not in this program, but if there's something that somebody wants to ask right now that would help you with the next couple of slides, please raise your hand. I'll bring the mic up. Oh, God, yeah, I forgot. These people are really smart. Okay. Go ahead. Go ahead with this one.
Let me just roll in.
And I have a question
good.
after this slide.
Super. So this is just talking about what I just talked about, which is that traditional neural networks, you can take stuff in, aggregate the information, you put it out. The nodes in a neural network, and when you get more of these generative AI talks today, it'll help fill this out a bit. The latent nodes, which are the ones that do the feature aggregation, they have, unless you're dealing with a long short-term memory, which is sort of artificial and hokey, but it works. They have no temporal memory. The transformer nodes actually, with that sinusoidal thing, they're looking into the past to find probabilistic combinations over history, like over all of Wiki, all of Reddit, all of the New York Times, much to the New York Times' general annoyance and dismay. Any source that could be gobbled up, they're looking for probabilistic co-occurrences of things that sort of match the input query, and then the successive rolling on generative results or answers to that query. But in each case, you get latent nodes that take in inputs. They cannot talk with their neighboring latent nodes. They just pass that up to management, so to speak. So it's like office workers that are siloed. Next slide.
Okay, just before you go on.
Yeah.
So if I understand you correctly, traditional AI training methods are deliberately narrowly focused and unable to recognize potentially important data and relationships. So, is there any way we can broaden AI perceptions without it just turning into a broad-based, so broad that it turns into chaos?
Well, okay, so that's a great question. It's the kind of question that a person would intelligently frame, having looked at that last slide. And the concern would reasonably be, if we try to change things, is it all going to like go to chaos, as you said? Right now, the methods that we have are all designed to give each node in that latent layer, the nodes that do the feature detection and learning. When we talk about training a neural network, that's what we're doing. Each latent node is like an office worker that learns to specialize on one specific job, and they have to function in isolation. The notion that we're introducing with CORTECONs, which I think is going to be a breakthrough here. Fancier equation, but more capability. And the essence is that these office workers, first of all, they get to team up a little bit. They get to talk across that cubicle barrier to their neighbors. And if they're getting sufficient input, and if, here's the engineering part that gets so cute and tricky and subtle, but if you're changing the governance parameters so that you're saying, hey, now is a good time to cluster up to form teams. So they can all sort of huddle. You can get these little huddles, these little teams, and the teams can even talk with each other. This ability to cluster, to team, all responding in different ways, but more than one node can respond to an inquiry or specific kind of feature. And then secondly, they can persist their memory. So more stuff is coming in, and some of the nodes are going to drop off and different nodes would pick up. But when you have a cluster, somebody from that cluster can stay active and keep that thread of memory going on. And that means that you can persistently contribute an activation to the ontology. And the game is all about activating the ontology. I don't even have slides here on it. It's one of those things that, is the next great meditation. What we need to do, and Lee, can we take a look at the next slide? Not
Oh,
to show.
sure. Yeah, and just while I'm here,
Yeah.
when we were talking about this and I was trying to get it into my head, I was reminded about the fact that as many of you folks here remember, when you go to a really good technical conference, a good significant amount of the value of what you get out of it isn't in the presentations. It's the people you bump into in the side conversations you have in the halls and over coffee. And so this just was a big revelation to me, that my God, we're going to let these things talk to, elements of the, have side conversations. I'll shut up now.
No. That's the most important thing is communication. It's the radical new breakthrough. It's the different kind of neural network architecture. And these are just like background notes. Look, if you're interested in this, YouTube's plenty of them, enough to fill in the blanks and get you totally up to speed with CORTECONs. There's research papers published, there's blog posts, there's all kinds of resources if you want to do research on this. If you actually, well, heck,
Since
download
we're
the code.
sticking, go ahead, keep going, and then I've got actually have a question from the audience.
Go ahead, jump in.
Okay, hold on one second.
Hi, thank you.
Wait.
All right, thank you for the opportunity to ask a question in great presentation so far. So pardon my ignorance, I'm fairly new to learning the theory of generative AI and things like that. So from what I've gathered so far, there are two parts, right, that I've understood, which would be needed in order to achieve the AGI. One is the context, which I think you're referring to as the ontology, and then the second is persistence, memory persistence. So if a neural network has the ability to continue to learn, right, that's one of the concerns, right? If you want to use a neural network, you don't want it to learn your proprietary information, working for a company or whatever, right? Yeah. But if the neural network has the capability to continue to learn from every input that comes in, would that at least address the issue of persistent memory, or will that?
Oh, okay, super question. And it's the kind of question where an informed person who's coming into the field would very intelligently ask. That's the right thing to ask. The whole intention with neural networks, and Stephen Grossberg, one of the earliest people in the field, was clearly elucidating this. And when you read the works of the earliest neural networks researchers, they were really clearly addressing exactly what you're questioning right now. So that question is so important. It's so fundamental. Beautiful question. Okay. What we've learned to do with neural networks was that we had the training phase and then the actual operational phase. So all the learning, and that would include what you would present of different training examples over time, which would adjust the connection weights. That's the long-term persistent memory. So the long-term persistent memory gets encoded into the connection weights. And once it's encoded, it doesn't change. I mean, there are newer neural network variants, but they're a little bit just trying to make tweaks to that, so to speak. And then the operational neural network has fixed weights, and you put stuff in and it responds. Is that the right? Is that what you're asking? It's partial.
Perhaps I missed the answer a little bit, right? Which is what I'm looking for was if I had.
Yeah, and we got to keep this short, so we got to keep moving on. But
yeah,
I want to make sure. Okay, I'll keep it very quick, right? So where I was trying to get to was, if I could, in a way, right, have the neural network learn from every bit of information that comes in, like our brains work, would that address the issue of the persistence, the memory persistence from a short-term perspective as well as from a long-term? So not do it periodically, but do it continuously.
Okay, Lee, could you restate the gentleman's question, because there's a little bit of garble in the audio feed.
I'm going to have to. He was saying that the human brain seems to work a little different, that there's persistence.
Oh, God, yeah.
Yeah, where I'm trying to go is so as a human being, right? As new information comes in, we continue to make those connections, and the network continues to develop in our brain, right? Which then allows for the short-term and the long-term learning of the brain. So if we could emulate the same thing in a neural network on a computer, would that solve the issue of the persistence, memory persistence that you're talking about?
Well, this is a step moving in that direction. So, instead of trying to give you depth here, let me ask you to go to the Femisys Incorporated YouTube channel. I'm truly not trying to shill, but uh, a YouTube on Steve Grossberg. Lots of YouTubes dealing with Carl Friston, who's dealing with the free energy principle in the brain. The whole CORTECON thing. There's a recent-ish, like maybe 2 months old YouTube on neurophysiological basis for AGI. That's probably the one that you want because the blog post that links to that accesses some of the top mind shifting stuff in neurophysiology that should inspire the next generation of neural networks. So check out those 3 resources and you're going to get a truckload of good stuff. I mean, just like a very yummy afternoon of like, ooh, good stuff.
And some of it seems to be talked about here in the slide you got, right?
Somewhat, yeah. So,
So just go, can you walk us through this slide?
oh God, how much time do we have, Lee?
We got 20 minutes and, so we're gonna have to balance between the two. But I think this one's important in the sense that this sort of shows temporal persistence and the ability to support crosstalk, right? I mean,
Yeah.
so go ahead.
Here's the thing.
Oh, or are you done with the slide? I can move
Well,
on.
let me just take 1 minute on this. Okay, that funny looking grid in that box. Okay, that is the nodes, the latent layer in this new kind of neural network. And on the bottom, you're seeing inputs into it, and on the top, you're seeing outputs. So it's kind of like a traditional neural network, but the nodes are laid out in a very specific pattern that makes the statistical mechanics, the stat mech, work. And it's a slightly different tweak on that well-known and well-loved basic statistical mechanics equation that is the foundation for all generative AI. It's a little tiny bit more complicated,
Okay.
but it's what allows the crosstalk. So rather than take us into that here with the limited time that we have, and we want to have room for more audience questions,
Yeah.
let me invite you. Femisys itself, resources, Femisys Incorporated YouTubes, lots of stuff.
And they're at all different levels. I mean, while I was briefing on this, I got through it. And so if I can understand it, I have great confidence he will. There's even one really great little video where she uses a fish sandwich, composed of 2 different types of fish, to explain the function of CORTECON, and it's just worth seeing for the heck of it. So before we move on, we got one more question I've got here is
Okay.
your approach appears to get around a lot of this siloing and misconnections that conventional LLMs suffer from. But how would that work in the real world? Can we do something with that?
Okay, good question. Perfect lead into this next slide. Thank you. Oh, God, love you. So here's the thing. It's going to be a painful transition, okay? To actually, if it was easy, it'd have been done. If this was at all the easy solution, we wouldn't have been going from billions to tens of billions to hundreds of billions to a trillion parameters, because that is a humongous investment of computers and people time in working with these things. And it's sort of mind-blowing. And that is easier than actually going back to the drawing board, which is what we have right here, and saying, okay, we've got to make this connection work. And to make the connection work, we need to have things like a control loop to control what's going on, because that baseline CORTECON thing, it's only 2 parameters, but it's a pure hardcore physics 2 parameters thing. And some of the physics needs to be, we need to create data tables. That's a near-term objective, kind of like creating log tables, but nobody's done it before. And then we need to actually figure out how we're going to control the activations in there. There's some hardcore physics that needs to get done as a preliminary. We're going to publish that stuff openly because, there's no use in trying to hold that secret. And by the way, at this stage, we're open to people joining in and doing science projects with us, truly. And when I say, do this, on your spare time around the house. It's like, this is the kind of thing you can do. This is absolutely the precursor for real AGI. And you can get involved at so ground floor right now. I mean, the code's available. Preliminary experiments are worked out. So you can just get up to speed. If this is your kind of idea of fun, you can be playing with this as soon as you walk out of the room today. So let's take that next slide. Once you get the CORTECON, which will interact with the ontology, basically worked out, there are internal, more subtle controls that are needed on things like how long do you want a particular node to stay active? Like how long should it be remembering something before it says, okay, I'm done with that task. I'm going to be ready to move on to something else. And you see in that upper right-hand corner, that bit about reasoning. Okay, we don't get to reasoning until we get the signal layer, the questions, moving into the CORTECON, moving into the ontology, where, for example, you would simultaneously activate Mini Coopers as being a kind of car with dimensions, and Great Danes as being a kind of dog with dimensions. And then the question comes in that asks about a comparison of dimensions, a size. That's a reasoning. That's a common sense reasoning thing, which is so not trivial, because you've got to be able to dig in there and find the relevant sizes. And hey, guess what? I was trying to like pretend that I was in that role. Well, they report the height, width, length dimensions of a Mini Cooper. They report a typical height for a Great Dane, but they're not giving you the breadth across the shoulders. They're not giving you the typical length. They give you a size in weight, typical weight. Your reasoning would have to do a whole lot of thinking and conversions to come up with enough basis for comparing that Great Dane against the Mini Cooper. Common sense reasoning is not easy. It's a big job. Now there's 50 years or more of work on common sense reasoning, but it's got to access an ontology. Okay, so none of this is trivial. You just got to be able to go from all that signal layer stuff, all the stuff in large language models and queries and such, up through something that matches to ontology, that accesses common sense reasoning, and then, and this thing I think is going to lead into what you want to ask about later, Lee, that goals and meta controls,
We've
mega
got about-
controls, meta,
yeah.
both.
We got about, a handful of minutes if we want to keep some questions.
Yeah.
So, okay, shall I move on? Next slide or
Oh, say again.
next slide?
Absolutely. Okay, last thing. If you've heard it all about Carl Friston, who's been described as the most cited neurophysiologist, most cited, and some people think that he's on his way to a Nobel Prize. And he's the guy who got me into thinking about free energy, neural networks, modeling the brain. And one of his earlier works, we're talking well over a decade ago, he starts modeling the external world as psi, Greek capital letter psi, and then your system that's doing the modeling of it as this thing inside the black box. And that's one of the things that we want to do. And that leads into something that Lee brought to my attention. God, Lee, was this several months ago at least? We were talking about all of this, and
Yeah.
you brought up Asimov's law of robotics, three
Oh,
laws of
yeah.
robotics.
Yeah.
And you don't get to that until you can make that distinction between this is self and how I interact in my environment, and this is the environment. So to be able to get to even having a sense of,
So
anything beyond, go ahead.
this is sort of a rudimentary proto form of self-awareness then, or
Rudimentary, but you've got to be able to know where you leave off and what you can get information from and what you can touch, and impact begins. Yeah.
yeah, because up to this point, it's just been kind of a bunch of stuff floating around in RAM. Okay. Next.
Yeah. So, alrighty. For us, if we want to actually start building AGI, the first step is the court. You got to make that signal level and the symbolic level communicate. And it's going to be CORTECONs, or somebody's going to have a different invention, but they're going to have to serve the same purpose. So why not try it with CORTECONs first? The theory has been worked out, so to speak. So if you would please on your
Hello.
own. I think we've got the next slide.
Yep.
Ah,
And
background about me.
Yep.
I
It's
tend to invent.
interesting, but
There we go.
there we
Yeah.
go. Here's where you can copy stuff down, and again, if you have problems grabbing it, I'll give you my card.
There we go. There's resources. You can get the very preliminary code because the thing that's taking us time right now is we're slowing down to build the YouTubes, build the blog posts, put together little demos so that basically the whole community can get involved because
Okay.
it's just too much fun. We don't want to keep it to ourselves.
I'll leave it up for a second, and then we'll get you to your special. And if you now, by the way, we are also offering a set of steak knives with this special offer.
Okay, so to get any office, because we tend to send out weekly emails unless I'm so immersed in grading student papers that nothing else is happening. But go to themesis.com, hit that about button. That will take you to themesis.com/themesis. And from there, we can see that next slide. Fill in the opt-in form, share an email address, and you start hearing from me.
And our operators are standing by if you I'm gonna move on to questions, but feel free to override if you had anything else you want to say, Dr. Brennan.
I'm good.
Okay, hold on, we got a question.
Okay, first of all, thank you for this presentation. I want to key off of one of your earlier pictures with a great name. So one of the issues that I have when I use transformers is that if I ask it for a series of citations, so scientific citations, it will proceed to go and give me an arbitrary set of names and followed by a somewhat title that's taken from elsewhere. In other words, no context. This is different from getting a list of people who could attend Trade Computer Festival. So does your process solve this? As an aside, this is probably similar to getting pictures of starfish, which can have any number of arms, versus pictures of human hands, which have to have 5. In other words, what does this do for context?
Okay, and I'm catching most of that, but again, a little garble on the audio. So Lee, can you translate the question?
No, I'm gonna hand it back to him. He's smarter than me, and I don't dare.
First of all, thanks, Lee. Okay, so the examples I gave you require context.
Yeah.
You have to know a human is a human, and they usually come with 5 fingers on each hand. The starfish is different. Does your method require additional information saying, here's the universe of people, and we're going to define them to have that many fingers?
Well, okay, good. This is the kind of thing that properly gets resolved when you have your question getting ported up to the ontology, and the ontology is where you keep information about human beings on the one side and starfish on the other, right? So it's not trying to look through, a gazillion series of Reddit posts and wikis on human beings and fingers and starfish. It's going up to the stored encyclopedic knowledge that is, relatively speaking, most of the time stable. And when you describe a human and you describe body parts, typically a human will have the 5 fingers. And then when you have a starfish, it will have its 5 little, what do you call them? Star nodes or whatever. And then you're asking really a common sense reasoning thing, which is going to have to be able to go in and compare 2 ontological elements. So it's going to have to drill down into the attributes associated with object classes, where the object class is respectively human on the one side, starfish on the other. And it's got to be able to drill down, and it's got to be able to find those slots of stored knowledge, kind of like finding the population of Trenton versus the population of Paris, so to speak. It's got to find equivalent matching stored bits, which is going to be a lot more stable and a lot more robust and a lot more reliable than trying to troll through a gazillion Reddit posts on and trying to figure out the relationship between human fingers and starfish. Because that's just probabilistic gobbledygook. Like, maybe it works, maybe it doesn't. When you get to the ontology, that's where you store your knowledge.
Okay, we got two questions. If is there anything else we need to sum up there? We got two questions to get through before we close out.
Okay.
Go ahead.
So there are hand-coded knowledge sets, and you cited Wikipedia, for example,
Yeah.
or databases that have been laboriously developed, and they represent ontological knowledge. But then there are large data sets. So, for example, you cited scientific papers that
Yeah.
have references that there's sort of a latent knowledge net there. Can LLMs sort of understand or pick up on these relationships that are not hand-coded, but are an inherent part of a lot of other data sets out there?
Okay. Really, really good. They are picking up on it in the sense of finding a signal pattern match. So, for example, you go to academia.org, I think it is, and you're looking at a paper and then it offers related papers. And it's doing that because it's doing an NLP, natural language processing kind of comparison of the content of the paper with content of other papers, and it's looking for similarities. And that is typically generatively created, not stored in a ontological knowledge base, because it's looking for similarity matches. There's no intelligence, though, behind it. It's just a comparison of terms, not a stored register saying this is a common repository of knowledge and we have these papers that deal with these topics in sort of a topic modeling or set of resources on given areas. It's a different way of organizing knowledge and a different way of understanding knowledge. And for AGI, we've got to be able to move between the two levels.
Thank you.
Hi, good morning. I'd like to thank you for your very interesting talk. I'm wondering if you can give us a feeling for what your demonstrations look like. What kinds of things would we see if you're demonstrating what you've been able to produce at this point? So
Okay.
what would it look like? You could
At
give
this
us a
stage,
flavor for that. Yes.
yeah, at this stage, it's baby, baby, baby. I mean, it is so simple and so trivial because I'm trying to teach people the statistical mechanics of the cluster variation method, which is the core engine for CORTECON. And frankly, very few people know that stat mech. So I'm essentially teaching statistical mechanics with a really simple one-dimensional version, embedded example, code you can run with just a push button in Python. It is so easy, but you know, we've got to start from someplace. And then we're going to do another example there, and then we're going to start the two-dimensional. While I have code for that already worked out, examples worked out, those are in research papers in GitHubs, and that's not the easiest way for people to learn. So the immediate goal is to bring people into the community, so to speak, and give enough learning resources so that you can progressively evolve as you move towards this AGI capability. And the first big step is, once we get everybody stable and centered on how to work with the CORTECON, is to move into connecting to ontologies. I'd love us if we could do that as a group and not just, you know, a single isolated research community.
So I'm inferring that you're welcoming some collaborators to build up some demos.
Oh, yes.
Now that you got the math mostly worked out.
That's been the whole focus for this last year. That's why we've been doing the YouTubes and the blog posts and making the code available.
Maybe there's some folks here at Trenton State that would be interested. Do you have any concluding remarks? I think we're right. Good God, we're on time. I mean, like, whoa. Do you have any
Only thank
concluding
you.
remarks? And if there's a really burning question, we can probably, you know, risk pissing off the next speaker a little bit. Otherwise, we'll go through. Can we just give us a little wrap up or not? And I could just thank you and let you get back to your tea if you want.
Well, here's to you folks at Trenton. Thank you so much. And to everybody, especially those of you who've come in from the West Coast and are joining in via Zoom, especially again to organizers of the TCF. It's been such a pleasure to be with you today. And I think you're in for a fabulous track. It's all going to build together to give you a great understanding of generative AI, which is the top topic in the world right now. So thank you. Great having time with you.
Yeah.
Look forward to seeing you folks again.
Great.
Do
Well,
come over to Themesis, okay?
It's been a pleasure, and my brain is full, so I guess I better sign off now. Thank you so very much.
Been fun. Thanks, everybody. Bye now.